electronic circuits, and more generally they come up in the context of linear systems broadly. Complex numbers are a useful introduction to the idea of functions of a complex variable, which will be important later in this subject and also in follow-on subjects in EECS. Now, a complex number, which I will refer to as Z, and put a tilde over it to indicate that it is a complex number, just a reminder that we're talking about a complex number, can be written as A plus JB. Now, A and B are real numbers. J, which is the basis of the complex number system, is defined as the square root of -1, or equivalently, J squared equals -1. Now, you should all have encountered complex numbers somewhere else, in high school or in earlier mathematics here at MIT. You will probably, in those cases, have seen the complex number written as A plus IB, where little I stands for the square root of -1. We don't use that convention in EECS because I is commonly used to represent currents in electrical circuits. So to avoid that possible confusion, electrical engineers and others as well define the basis of the complex number system, square root of -1, as J. A and B are real numbers. J is the square root of -1. A is the real part of this complex number. And B is the imaginary part. Now, one of the points I will emphasize throughout this presentation is that when you're dealing with complex numbers, it's very helpful to think of them in terms of a graphical representation. That is, the complex number, A plus JB, is a point on a plane, a two-dimensional plane, in which one axis represents the real part and the other axis represents the imaginary part. This is the origin. The x-axis will represent the real part, and I will denote it that way, and the y-axis represents the imaginary part. So the complex number, Z equals A plus JB. Let's say this is A on the real axis. This is B on the imaginary axis. The complex number Z is out here. That is, this is Z tilde. It is a point in the plane which has an intersection on the real axis of A and an intersection on the imaginary axis of B. A very simple two-dimensional representation which comes up frequently and which it's helpful to keep in mind as you manipulate complex numbers. Now, the representation I've just shown you obviously is in rectangular form. You can equally represent that point in a two-dimensional plane as a number in polar coordinates. That is, if we draw again the complex plane, real axis, imaginary axis, the origin, and we had that number Z out here, Z tilde, as the complex number, instead of describing it in terms of real part and imaginary part, I could describe it in terms of the dimensions of a vector from the origin out to that point, a vector which has a length r and makes an axis with the positive real axis, makes an angle with the positive real axis of theta. This is the complex number in polar form. And to write it in polar form, we could represent it as z tilde is equal to a magnitude of r at an angle of theta. Conversion back and forth between rectangular form and polar form is pretty obvious. That is, if I drop down a perpendicular to the real axis and draw a line over to the horizontal axis, this corresponds to the real part, which I previously called A, and the imaginary part B. So the real part of this complex number, A, is just r cosine of theta, and the imaginary part B is equal to r sine of theta. So the conversion from polar form back to rectangular form is trivial when you think of it in graphical form, and the conversion the other way goes just the same. If you look at the vector from the origin to the point z, that vector r has a magnitude which is simply, by the Pythagorean theorem, the square root of the sum of the squares of the sides. So r is the square root of a squared plus b squared, and the angle theta is the inverse tangent of b divided by a. So a complex number z, to summarize up to the moment, can be represented in rectangular coordinates by its real part and its imaginary part, that is, as z equals a plus jb, or equivalently, it can be represented in polar form as r, the magnitude of the vector from the origin out to the point at an angle of theta. These are the two ways in which you can represent a complex number, and the conversion from one to the other is straightforward. If you have it in polar form, r at an angle theta, r times the sine of theta times the cosine of theta gives you the real part, r times the sine of theta gives you the imaginary part, and if you have it in polar form, in rectangular form, then the length of this vector r is simply the square root of the sum of the squares of the real and imaginary parts, and the angle is the angle whose tangent is imaginary over real. Now, I want to introduce at this point a new idea, and it shouldn't be new to you, but new in terms of this discussion, which we will make frequent use of in circuits and electronics, in fact throughout electrical engineering, computer science, and it is based on what is called the Euler Equation. The Euler Equation says that E being the base of the natural logarithm, not lateral logarithms, e to the j theta is equal to cosine theta plus j sine theta. And this relationship is referred to as the Euler Equation. Now, what are the properties of e to the j theta? Well, we may ask, what is the magnitude of e to the j theta? And we'll designate the magnitude of a complex number by a pair of square brackets in that form. The magnitude of e to the j theta is just the square root of the sum of the squares of the real and imaginary parts. Well, the real part is cosine theta squared, and the imaginary part is sine theta squared. And as you well know, cosine squared plus sine squared equals 1. So the magnitude of e to the j theta is always 1. The angle of e to the j theta is the angle which is the inverse tangent of the imaginary part over the real part. So it's the angle which is the inverse tangent of sine theta divided by cosine theta. And that is the identity, if you will, theta. So if we represent the Euler relationship on the complex plane, real and imaginary, we have a vector which has unit magnitude. The magnitude of the vector is 1. And it makes an angle with the positive real axis of theta. So this point represents e to the j theta. The Euler relationship. This proves to be very useful in this subject because we will use the product of complex numbers written in the form e to the j theta times another complex number, which will be of the form e to the j omega t, a time-varying complex number. We will represent the product of a complex number in the form e to the j theta times a complex number of the form e to the j omega t, and use that frequently in circuit analysis. It's helpful as you think about the Euler relationship to recognize that the locus of all the complex numbers represented by the Euler equation is a circle centered on the origin of radius 1. So this circle of radius 1 is the locus of e to the j theta as theta varies. Now, e to the j 0, angle of 0, obviously is just equal to plus 1. The vector lies along the real axis and has a value of 1. E to the j pi over 2, 90 degrees if you will, puts the vector along the imaginary axis, and so e to the j pi over 2 has a value of j. The basis of the complex number system, j multiplied by 1. E to the j pi, e to the j pi, 180 degrees, falls along the negative real axis, and the value of e, the magnitude of e to the j theta is minus 1. And finally, if I come around 270 degrees, 3 pi over 2, e to the j 3 pi over 2 is just equal to minus j. Those are relationships which will occur frequently, conversions back and forth between unity and the basis of the complex number system J, which you can think of in terms of the unit circle on a complex plane. Now, if we have a complex number at a different angle, say perhaps e to the j pi over 4, which corresponds to 45 degrees, about as I've drawn this, then this can be written in rectangular form as 1 times the cosine of pi over 4, which is square root of 2 over 2, plus j times the sine, and I will pull out the square root of 2 over 2 and write it simply as 1 plus j. Real and imaginary parts are equal. As you see from the diagram, if the angle is 45 degrees, the conversions back and forth are entirely straightforward. Now let's move on to some discussion of manipulation of complex numbers. Complex numbers, just like the world of real numbers, can be added, subtracted, multiplied, divided, raised to powers, taken roots thereof, and so on. How do we handle such manipulations? Well, let's look first at addition. And therefore, at the same time, at subtraction. Suppose I have two complex numbers, z1 equals a plus jb, and z2 equals c plus jd. And I want to form z3, which is equal to z1 plus z2. Got to put the tildes on hold here to keep it straight. Just indicate these are complex numbers, not real numbers. How do I form the sum z3 equals z1 plus z2? Well, it proceeds just as with real numbers. You add the real and imaginary components. When you sum the imaginary components, you put a j in front of that sum, and you sum the real components, and that's the real part of the sum. In other words, z3, the sum of these two complex numbers, is just equal to the sum of the real parts, a plus c plus j times the sum of the imaginary parts. And had we been subtracting instead of adding, of course, it would just be minus signs. You can easily represent addition or subtraction in the complex plane. Real part, imaginary part, and the origin. Suppose the complex number z1 is over here, and the complex number z2 is over here. So this is z2, this is z1. In order to add or subtract, I want to think of the number in terms of its rectangular coordinates, where this is A, this intercept is B, this intercept is D, and this is C. The sum of the two numbers has a real part, which is the sum of these two real parts. So the real part of Z3 is going to be less than, going to be closer into the origin than A, because C is negative. So the real part is going to be somewhere along this line, which has an intercept of A plus C, C being a negative quantity. And the imaginary part is going to be the sum of these two imaginary parts, b and d, so it's up here somewhere. And the complex number z3 then is here. One way of thinking about the process of addition or of subtraction is to imagine it as the addition of vectors. That is, if I draw the vector corresponding to z1 and the vector corresponding to z2, and then translate the vector z2 to the end of z1 and stick it on there, keeping it parallel to its original position and its original length. That is, this is z2 translated. It should end up at z3. My trigonometry here was a little bit off. The values don't quite add that way. But the principle is clear. That is, the sum of the real parts is the real part of the sum. The sum of the imaginary parts is the imaginary part of the sum. And in vector terms, it's just like adding vectors. Now, what about multiplication or division? And division. You can multiply complex numbers easily in either polar or rectangular form. If I take these two numbers again, a plus jb, and z2 is equal to c plus jd, then the sum, z3, equals, adding up, the product, z3. Forget that comment about the sum. The product z3, that is z1 multiplied by z2, is just writing it out, a plus jb times c plus jd. And if I do the cross multiplication, I have a times c as a real number. So ac appears in the real part. And if I multiply these two together, j times j is minus 1. So it's minus b times d, minus b times d. That constitutes the real part. And then a times jd is j times a d. And c times jb is j times b times c. And so the complex number can be written in that form, doing it in a rectangular form, with the numbers represented in rectangular form. However, if I represent the number instead in polar form and say this is r1 e to the j theta 1, and this is r2 e to the j theta 2, then the product z3 equals z1 times z2. Simply multiply them together. It's r1 e to the j theta 1 times r2 e to the j theta 2, which I can represent as r1 r2. The magnitude of the product is the product of the magnitudes, and the angle of the product is the sum of the angles, theta 1 plus theta 2. In writing this portion of the complex number, that is the Euler Equation portion of the number in polar coordinates, I'm making use of the fact that e to the a times e to the b is equal to e to the a plus b. a relationship you're all certainly familiar with. So when it comes to multiplication, and as you'll see in a moment, the division as well, it can be done in rectangular form, as you see here. The division of complex numbers can be done either in polar form or rectangular form. It's considerably simpler to do it in polar form. Let me illustrate that first. If we have the usual 2, z1 equals r1 e to the j theta 1, and z2 equals r2 e to the j theta 2, then the quotient, if we want to form a quotient, z3, which is equal to r1 divided by which is equal to z1 divided by z2, we simply express them in polar form. So we have r1 e to the j theta 1 divided by r2 e to the j theta 2, and z3, the quotient then, is equal to, has a magnitude which is r1 over r2. These are real numbers, that's their quotient, times e to the j theta 1 minus theta 2. In combining the two exponentials, I'm just taking advantage of the fact that e to the a divided by e to the b is equal to e to the a minus b, as you surely know. Now, in order to divide complex numbers in rectangular form, we need to introduce another concept. That is the concept of a complex conjugate. Let's think about z1 and write it in rectangular form. z1 is a plus jb. The complex conjugate of z1, which I'll indicate with an asterisk, meaning conjugate of, is by definition, this is a matter of definition, a minus jb. This is a complex conjugate. The complex conjugate is such that when I take the product z1 times z1 conjugate, let's just multiply this out in our heads here, I won't write it down. I get a times a, which is a squared, and I get jb times minus jb. J squared is minus 1. The minus sign makes it plus 1. So I have a b squared, a squared plus b squared. And then I have j times minus j times a times b. And from this cross product, plus j times a plus b. So the imaginary parts cancel. And the product of a number, of a complex number and its complex conjugate, is a real number, which is the magnitude of the complex number, r1 here, squared. If you do that multiplication in polar form, z1 complex number times z1 conjugate, you get r1 e to the j theta 1 times r2 e to the j minus j theta 1, which just is r1. It should be r1, I'm sorry, we're talking about the complex conjugate, r1 squared. Now, taking advantage of that property of complex conjugates, that if you multiply a complex number by its complex conjugate, you get a real number. I'll show you how to do division in rectangular form. Z1 is A plus JB. Z2 is equal to C plus JD. Now, if I want to stick entirely to rectangular form and form the quotient, Z3 equals Z1 divided by Z2, I have to do something with A plus JB divided by by C plus JD. How do I get rid of the complex number in the quotient? If I can get rid of the complex number in the denominator, pardon me, if I get rid of the complex number in the denominator, then I have something which is in the form of a complex number alone in rectangular form. Well, the way to do that is to multiply this complex number, numerator and denominator, by the complex conjugate of the denominator. So I multiply by C minus JD over C minus JD. That clearly doesn't change the value. This reduces to 1. But I then end up in the denominator with the number times its complex conjugate, which is just C squared plus D squared, the square of the magnitude of Z2. And in the numerator, I have, for real parts, A times C from this cross product. From this cross product, it's BD times minus J squared. Minus J squared is plus 1, so it's AC plus BD is the real part. And the imaginary part, plus J, has two parts as well. If I take the cross product A times minus JD, it's minus AD, so there's going to be a minus AD term here. And then if I take the cross product C times JB, it's going to be CB times J, C times B with a plus sign, minus AD, close the bracket. So there it is, division done in rectangular form. And the way to do it is to rationalize the denominator, to convert the denominator to a real number by multiplying numerator and denominator by the complex conjugate of the denominator. Now that's the conclusion of this review of complex numbers. Let me go back and just emphasize the principal points. A complex number can be represented as A plus JB, a real part plus J times an imaginary part. A and B are real numbers, and J is the square root of minus 1, or J squared equals minus 1. It's helpful to visualize all complex numbers in the complex plane, which in rectangular coordinates takes that form, and in polar coordinates takes this form, where you represent the complex number Z, not in terms of its real and imaginary parts, but in terms of the length of the vector from the origin out to Z, and the angle that that vector makes with respect to the positive real axis. And you can write it as Z equals R at an angle of theta. The conversions back and forth between polar and rectangular are trivial, involves a little bit of trigonometry. But the most convenient way to represent that complex number in polar form is in terms of the Euler equation. E to the j theta equals cosine theta plus j sine theta. This is a complex number, obviously. It is a complex number which has an angle theta and which has a magnitude, a value of the vector, the length of the vector, of 1. It is the unit complex number. And so as theta varies, it has a locus which describes a circle of radius 1. And for various values of theta, the resulting complex number expressed in rectangular form has a value which is readily calculated just by taking the sine and cosine of the angle that's involved, the angle theta. Didn't put it on here before, let me put it on now. This is the angle theta. And these four particular ones are the ones that correspond with the vector lining up with the positive, negative, real, and imaginary axes. If you don't understand these identities, then think about e to the j theta a little more. Addition of complex numbers is best accomplished with them in rectangular form. Addition or subtraction, multiplication, and division are most easily done with the complex numbers in polar form. That, my friends, is the end of this review. I emphasize that this is intended to be a review of material which you are expected to have studied somewhere else in high school or earlier in mathematics here. And I go through the review, have illustrated these manipulations and these representations because the concept of manipulation of complex numbers arises very soon in the subject, and it is helpful to be facile with the manipulation of these numbers. If you spend time figuring out how to multiply and divide complex numbers or how to add and subtract them when working on a circuit problem, it is going to be just that much harder to get to the electrical engineering end of it. Thank you.